One more topic. Ionic radius. Again, you would doubt that we just talked about ionic radius, but we need to talk about ionic radius again. But this time, it is going to be a little bit more challenging. I'm sorry, but we need to talk about it, right? Chemistry. In this topic of ionic radius, we are going to talk about ionic radius of ions, not atomic radius. Previously, we talked about atomic radius, where a neutral element, how much of distance it is experiencing from its center of the nucleus to the valence electrons. Here, we are going to talk about once a neutral element forms an ion, either by losing an electron or by gaining electron, what is the effect of that change of number of electrons for that neutral element? Either it's going to lose the size of its atomic radius or going to gain the size of its atomic radius compared to its atomic radius. Okay. Whenever an element either lost or gain electrons, there is obviously going to be a huge change in its radius that we call it as ionic radius. So here, if you see the list, well, before I show you the list, I will show you this example. So here, what you're seeing at the bottom of the screen on left side is a electronic configuration of the sodium before and after, and its radius in its atomic size, in its atomic shape, and it's in ionic shape. So when the sodium is in neutral, you can see that in the top, in the left side, it has a total 3 shells, 1s2, 2s2, 2p6, and 3s1. It has 3 shells, 3 shells means larger, right? Whereas once it forms the charges Na+, it lost an electron from shell 3s, only electron in shell 3s, which means it lost an entire shell. You can clearly see that the size of the Na+ is clearly smaller than the size of the neutral sodium, because by losing an electron from its only electron from the outermost shell, the sodium plus lost an entire shell. So ionic radius of Na+ is much more smaller than the ionic radius of neutral sodium. So we are going to compare the atomic radius of the neutral elements with the radius of the ionic of the same element several times. So let's do it. Here you can see the trends. Lithium, when it is neutral, it has atomic radius of 152, but once it forms ion, it has atomic radius of only about 76. Sodium, we just spoke about it in an example below. It has atomic radius of 186, but ionic radius of 102. Again, ionic radius is same. Ionic radius is calculating the distance from the center of the nucleus of that particular element to the outermost valence electrons. But when it is an ion, it either has less or more electrons depending on its preference on the periodic table. Like metals would like to lose, non-metals would like to gain, which means metals always forms cations, which means positively charged species by losing an electrons, but non-metals would always form anions because they would like to gain electrons, because if they gain electrons, they would release electron affinity values by losing the energy. So clearly, this trend in here is divided into metals and the non-metals, right? So here even though you can, we already know that from top to bottom, atomic radius increases. You can still say the same from top to bottom, even ionic radius increases, but it's not what we worry about here. Here, what we worry about is either you can understand that when a element loses an electron, if those electrons are from outermost shell, its ionic radius is significantly going to get smaller. Here, if you see, we're only discussing selected a few examples from group 1A, 2A, and just one example from 3A. Basically, we are discussing main group elements. If they lose enough number of electrons to be isoelectronic with the noble gas electronic configuration, we are going to say that their ionic radius is going to get significantly smaller because they are going to lose entire shell. All of these elements here on the left side that are in blue color, all of them are metals from group 1A, 2, and 3A. All of them are losing respective number of electrons to reach the isoelectronic configuration with its previous noble gas. So which means you're forming +1 charge. It did not include, so I'm just writing +1, +1, +1, and all the elements in 2 are going to lose 2 electrons. Only then they are going to get this small really. So if they form those charges, those ionic radius are going to be much more smaller because they would lose an entire shell. So let's talk about the elements on the right side. Elements on the right side are non-metals here, group 5A, 6A, and 7A. And you can see that their ionic radius are actually increasing. So for metals, right here, atomic radius is smaller than ionic radius, but for non-metals, atomic radius is greater than ionic radius for metals, whereas for non-metals, atomic radius is smaller than ionic radius. Let's discuss why. So non-metals, when they were ready to form ionic form charges or ions, they have the only way they can do it is by accepting electrons, because they were, first of all, non-metals in general, they do not like to lose electrons, and also because their Z effective is larger, which makes the element smaller, which increases the attractions between central nucleus and the outside valence electrons, which means it is not an option to lose an electron because they were really small elements. So only option is accept more electrons. So because of the strong powerful Z effective, they accept more electrons. So once they accept the more electrons, the stronger Z effective of the nucleus can keep that electron in its valence shell. But only problem is that added extra electron creates additional multiple number of electron-electron repulsions, because we know that similar charges repel, right? Here you can see a clear example of how much it would repel. Adding that extra electron makes these already existing electrons in its outer shell go repel them against each other in much larger fashion, which swells the size of the radius of the ion. That's why a neutral atomic radius of a non-metal is going to be much more smaller than the ionic radius of a non-metal once it forms the anionic charge. So here, if you can see, atomic radius of sodium is only 75, but once it forms ions, it will have a greater ionic radius compared to oxygen. Again, it has only 73 ionic atomic radius, but it has the ionic radius of 140. Even fluorine, it has the atomic radius of 72, but it has the ionic radius of 133. See, it's getting larger because by adding that extra electron, you're creating more electron-electron repulsions. You can see same trends that are happening from atomic radius to ionic radius increase, increase, increase. So similar trends. Basically what we have here is what I just discussed in last slide for a long time. From here, what we are going to talk about is general regions of the periodic table,